This is the first video of a series on vectors. We'll introduce vectors in two dimensions. That's on a set of x and y axes. Some quantities only have size, that's magnitude, how much there is of something, for example, an amount of liquid in terms of its volume, or how far you go in terms of distance. These are scalar quantities that only have size. Vector quantities have size and direction. For example, you exert a force in a certain direction. Velocity is the speed you travel in a certain direction. To show a vector in maths, we draw a line of a certain size, that is length, and in a certain direction. So this vector here, vector u, is heading off in a particular direction given by this arrowhead. Vectors in textbook are printed in bold type. Since we cannot write that very easily, we write the letter with a line under it, and that reads vector u. We use a lowercase letter for vectors, so that's vector u. So this line has a certain size, and it's got a direction, and that makes it a vector quantity, the fact it's got a direction. Because we're working in two dimensions with x and y axes, that's the x direction horizontally and the y direction vertically, we can give the vector as a column vector, where we say the number of units you move horizontally in the x direction. This letter A represents that, and vertically in the y direction, the letter B represents that, and it's written as top number A, the x component, and bottom number B, the y component. So that's the horizontal A and the vertical B, x direction A, y direction B. So this is in component form, because these are components, x component and y component. So this is a column vector and it's in component form. So here's an example. To go from A to B, 3 units to the right, 4 units up. So as a column vector, that's 3, 4. 3 in the top, 4 in the bottom. There it is there, written as a column vector in brackets, 3, 4. Call that vector u. This point A and this point B on the line, that's a line AB heading in a particular direction, is written as AB with an arrow above it, and it's read directed line segment AB. So it's a line AB, but with the arrow above it, it becomes directed line segment AB. It's 3, 4 as a column vector, but CD is also 3, 4, and EF is also 3, 4. So these 3 different directed line segments are all equal to 3, 4. So the vector 3, 4, which is vector u as it's labelled here, is represented by these 3 different directed line segments. So it's one vector, 3 different directed line segments. So that's directed line segments, capital letters, because it's point A and point B, and you're moving from A to B, or you're moving from C to D, you're moving from E to F. So you've got to get the direction correct. You can't write BA, it must be AB, because you're starting at A and finishing at B. And they are the same vector because they're the same column vector 3, 4. If the components of a vector are the same, it is the same vector. If the components are different in any way, sign different, or numbers different, you have different vectors. Here are some examples. We get vector A here. To move from one end of this line to the other, you have to go 5 boxes to the right in the x direction, that's positive 5, and then 2 down in the y direction, that's negative 2. So it's 5, negative 2, 5 to the right, 2 down. For B to move along the line here from one end to the other, we go in the x direction, 3 to the left, that's negative 3. In the y direction, 4 down, that's negative 4. So it's negative 3, negative 4, 3 to the left, 4 down. C here, to move from one end of the line to the other. That's moving along the vector. 3 to the left, negative 3 in the x direction, 5 in the y direction. So there it is, negative 3, 5. D, you're moving 5 to the left in the x direction, that's negative 5, and 0 in the y direction. So that's negative 5, 0. And for E, you're moving 0 in the x direction, but you're moving positive 5, that's 5 up in the y direction. So that's 0, 5. Now, these are the same vectors down here, and I've simply put letters on them, capital letters for the ends of the line. That's point A and that's point B. So this is a directed line segment AB. It's the same vector as up here, it's 5, negative 2 as a column vector. This is DC, moving from D to C, so it's written as DC, and it mustn't be written CD, which would be the wrong direction. EF, HG, and IJ. So you've got to watch the order of the letters. This is starting at A, finishing at B, starting at D, finishing at C. So you've got to follow the correct direction. These are simply directed line segments, and they are representatives of each of these vectors. So the same vectors involved, same components, same vector. Different components, different vectors. This is directed line segment PQ. It's a representative of vector V. To go from P to Q, it's 3 in the x direction to the left, that's negative 3, and 4 up in the y direction, that's positive 4. There's the column vector, negative 3, 4. That's vector V. If I were to reverse that arrowhead, so it goes in the opposite direction. Now I've drawn it separately because it would clutter the diagram, so I've drawn it over here. That's reversing the direction of the arrowhead. You're now going 3 to the right, 4 down. That's positive 3 for the x direction, negative 4 for the y direction. There it is there. That's the negative of vector V, the reverse direction. It's now QP. Instead of PQ, it's QP. So the letters have reversed. So notice the direction is reversed, the letters are reversed, and also the components reverse sign. Negative 3 became positive 3. Positive 4 became negative 4. So when the direction is reversed, the letters got reversed, the components reverse sign. The components get multiplied by negative 1. So QP is the negative of PQ. So when you reverse the letters, you're getting the negative. That's why the letters must be written the correct way around. And to get the negative, simply switch the signs on the components. When it's the vector V, to show it's negative, just put a negative sign in front. So that's from reversing the arrowhead there. So here are some examples of directed line segments. Going from A to B, we travel in the x direction 6 to the right, that's positive 6, and the y direction 2 up, that's positive 2. So there's the component form, 6, 2, that's vector 6, 2, column vector. The directed line segment is AB, you're going from A to B. Here we're going from D to C. So when we go from D to C, we're going positive 3 in the x direction, positive 5 in the y direction. There it is, 3, 5, and it's going from D to C. This one, we're going from E to F, so in the x direction, we're going 7, positive 7, and then negative 3. That was 7 to the right, 3 down, going from E to F. Here we're going from H to G, so we're going 3 to the left, that's negative 3 in the x direction, and then upwards 5, that's positive 5 in the y direction. So that was negative 3, 5, and I'm going from h to g. Here we're going from I to j. So here we're going 6 to the left in the x direction, that's negative 6 in the x direction. 1 down here, negative 1 in the y direction. So it's negative 6, negative 1, 6 to the left, 1 down. K to L, well here we're simply going 6 to the right, positive 6 in the x direction, but we're not going up or down, nothing in the y direction. So it's positive 6, 0, going from K to L. Going from M to N, we're going 6 left in the x direction, negative 6 in the x direction, and 2 down in the y direction, negative 2 in the y direction. So that was negative 6, negative 2. And we're going from M to N. Here we're going from Q to P. So it's QP. We're going 0 in the x direction, and we're going up 6. So that's 6 in the y direction. So that's 0 for the x direction, 6 for the y direction to get from Q to P. Finally, S to R. So here we're going to the left, 7. That's negative 7 in the x direction, and then 3 up. That's positive 3 in the y direction. So that's S to R. So these are column vectors. None of them are identical in components. So they're all different vectors. None of them are the same vector. However, if you look at AB being 6, 2 and MN being negative 6, negative 2, this vector MN is the negative of AB. Same here with EF where it's 7, negative 3 and SR's negative 7, 3. So SR is the negative of EF because the components are switch signs. So it's simply the vector here has its arrowhead reversed, you get this vector. So that's a column vector 7, negative 3. It's the negative of this vector, negative 7, 3. This is a vector 6, 2. This is the negative of that vector. This is negative 6, negative 2. Now come on to the size of the vector, which is pretty straightforward because simply if you have component form, it's part of a right angled triangle. The size of vector u here is written with 2 vertical lines on either side of it, and it's read the magnitude of vector u. That just means the size of vector u. And it comes from Pythagoras' theorem. That's the hypotenuse in a right angled triangle. So the magnitude of u squared is equal to a squared plus b squared. So the magnitude of u is the square root of a squared plus b squared. So the rule is to get the size of the vector, square the components, add, and take the square root, and it just comes from Pythagoras. There's a directed line segment AB, components negative 3, 6. If you want the size of AB, that is the length of the line AB, the magnitude of directed line segment AB, or the distance between points A and point B, square the components, add and take the square root. So there's the magnitude, the size of AB. Now that's equivalent to the line AB. It's square the components, add them, take the square root. 9 and 36, which is 45. Square root 45. Simplify surds. Separate videos on that if you haven't looked at that before, but whenever you get an answer from Pythagoras' theorem and it's a square root and it's not an exact answer, it can sometimes be simplified. This can be written as root 9 times root 5, which will then become 3 root 5. So the size of the line there, represented by AB, is 3 root 5. The distance between point A and point B is 3 root 5 units. These vectors are all different vectors because the components are different. However, they've got the same magnitude because 3 squared plus 4 squared, square root it, is 5. Square root of 4 squared plus 3 squared is 5. Square root of negative 3 squared plus 4 squared is 5, and same with this one. So you square the numbers, you add, you take the square root, you're going to get the same answer each time, 5. These are all 5 units long, but they are different vectors. They're all heading in different directions, although they're the same size. So they're different vectors, but they've got the same magnitude. So here's an example. Here's a vector A. If you have to calculate its size, what you do is get it in component form. So it's in the x direction positive 2, in the y direction it's positive 4. So vector A is in component form 2, 4. That's a column vector 2, 4. To get the magnitude of A, take the components, square, add, and take the square root. So the magnitude of A is 2 squared plus 4 squared, and root it. That's 4 and 16 is 20. Root 20, it's a surd. Simplify it. Square number 4 goes into it. 4 5s are 20, so it's root 4 times root 5, which is 2 root 5. So surds always get simplified. Separate videos on that if you haven't met it before, you need to revise it. Here's another example for B here. So to go from one end of the line to the other, you're moving to the right 6 and then down 3. So it's positive 6 for the x, negative 3 for the y. So vector B as a column vector is 6, negative 3. To get its magnitude, square the components, add and take the square root. So that's 6 squared plus negative 3 squared, and then square root it. That's 36 and positive 9. That gives you root 45. That's root 9 times root 5, which is 3 root 5. So that line has a length 3 root 5 units. So a vector, write it in component form, and you can get its magnitude quite easily. So if you want the distance between 2 points, you can get the directed line segment AB as a vector, square the components, add and take the square root. So how do you go from negative 1, 2 to 7, 6? The x direction is from negative 1 to 7 is 8 units. So you've travelled 8 units in the x direction, from x being negative 1 to x being 7. So the x component is positive 8. In other words, if you look at the coordinates, from negative 1, you need to add on 8 to get that 7. And in the y direction, you've gone from y coordinate 2 to y coordinate 6. That is, you've added on 4. So to get the component form of the vector here, look at the x coordinate of the first point and think what you have to add on to get the x coordinate of the second point. You have to add on 8. And look at the y coordinates and do the same. To get from 2 to 6, you have to add on 4. So the column vector's 8, 8, 4. There it is. That's negative 1, add 8, you get 7. And y coordinate 2, add 4, you get 6. So just think, what do you add on to the x coordinate, and what do you add on to the y coordinate to get the end of the line? And the magnitude of AB, that's the size of directed line segment AB, is 8 squared plus 4 squared, and take the square root. 64 and 16 make 80. That's root 16 times root 5, which is 4 root 5. So that's simplifying the surd at the end. So get the component form, square, add, and take the square root. To go from C to D, you're going from x coordinate negative 2 to x coordinate 5. That needs an extra 7. So the x component is of the vector is 7. And to go from y coordinate 4 to y coordinate 3, you subtract 1. So the y component is negative 1. So the x component was 7 because you add on 7 to the x coordinate. And the y coordinate added negative 1 to the 4. So it's 7, negative 1. So that's negative 2, add 7, you get that 5. 4, add that negative 1, you get that 3. Now just square the components, add and take the square root. 7 squared, 49, negative 1 squared, positive 1, that makes root 50. That's root 25 times root 2, that's 5 root 2. So that's the size of the line AB, it's the distance between the points AB, it's the magnitude of size of the vector. All the same thing. And if you click the link in the description, there's a worksheet with answers where you can practice the component form and the magnitude, that's the size of the directed line segment. And it's done here with coordinates. And it's here coordinates again, but working backwards. And again here, component form and the distance between 2 points. And here it's parallelograms because opposite sides of a parallelogram are equal in size and they are parallel, so they are the same vector. So you can work out missing coordinates. The next video is on adding and subtracting vectors in component form and in by diagram. There's a set of notes. If you click the link in the description, the notes cover all the vector videos. So we've covered in 2 dimensions component form and magnitude, and the next video is adding and subtracting. Hope you found this video useful. Thank you.